We know that today's homes need to be built more energy efficient and healthier, but just how do we achieve that? In today's episode, we're going to get an up-close look on just how to do that. How to make a home more energy efficient, healthier, how to make your home more comfortable, and just plain all around better. Let's take a look. Arnold Lumber has been a partner of New England builders and homeowners for over 100 years. Our goal is to elevate projects to their highest potential through top quality product solutions and above and beyond service on all projects from start to finish. Now, we're teaming up with industry leaders and the area's best builders to give you insights on the latest material technologies, best practices, and unique projects. This is Breaking Ground. Well, it's a beautiful day here in Charlestown, Rhode Island, and we're back on the job site with Steve DeMetrick and his crew. And you may remember last time we were here, the house was really in the rough stage of building, working on putting in ventilation, working on plumbing and electricity. Today we're further down the road and we're going to take a close look at the house finished. With all the elements installed, we'll get a look at the things that make this house energy efficient, how they were able to achieve comfort and consistency from room to room, and in general, the process that it takes and the unique techniques to really make this house a better house. We'll also take a look at the exterior finishes with the exterior siding by AZEK Exteriors and the TimberTech decking on the decks and porches. Let's go inside and take a closer look. Starting from the ground up here in the basement, and I do remember you always start with the plans, not the basement, but here we are in the basement. Right. Walk us through, what are we working with when we talk about utilities for this house?
Number one with all of our houses is everything's 100% electric. There's no fossil fuels burned in the house at all. That's number one. Number two is we work really hard to simplify the mechanicals down to the essentials of what you need in order to we balance that with maximizing the comfort and the ability to manage comfort in the house.
Right, you don't want to skimp on any of the comforts and health values of the system, but you don't need to put in a monster system if you don't need it.
It's about appropriately sizing the system. So like we said, we start with design, we start with mechanical design as well. So we're insulating and air sealing and choosing windows. We'll change orientation, change overhangs to minimize the solar in the summer and maximize it in the winter. And when you take all that, you can actually do an energy model in a computer. And it'll tell you exactly what the heating and cooling loads are for the whole building, room by room. Wow. And we can actually change those values. When you use the energy modeling as a tool, you can actually use it as a design tool and a product selection tool for heating and cooling systems, ventilation, insulation.
Then you've got all your problems solved going into it. It's all figured out. You've done the whole model.
Yeah, there's no more rule of thumb. There's no more like, oh, that's what I did in the last house and it worked. Right. Well, every house is different.
Can you give us some examples of what to look at then, where you're showing us that maximization with what we need in this house?
There's a 2,600 square foot high-end custom home. This is it for mechanicals. You've got your ventilation system.
Yeah.
This system could heat and cool the entire house. It's only a 12,000 BTU air handler. And then we've got a hot water heater. That's it. The only maintenance on these is 3 filters. That has a filter. The water heater has a little filter in it. Right. And then this guy has a filter.
And that's the upkeep. So compared to a more traditional house utilizing fossil fuels, where you'd have your boiler, you'd have your hot water tank, you'd have your...
There's no chimney. So we don't need a chimney in this house.
There's no chimney, that's right.
There's no chimney to clean every few years.
It's a lot less maintenance, a lot more efficient, and frankly, a lot more space available in your...
We got a lot more space too. And part of thinking things through, like I was just doing a test at a house a few weeks ago, and I've got a picture of it. This person installed this heating and cooling system, and it was a heat pump just like this. Yep. And you notice on ours, we've got a whole house dehumidifier that's tied into it. Okay. So the time of the year when it's humid but it's not hot, you don't need your air conditioning. Right. That runs, and that lowers the humidity in the house, and it's perfect temperature
without cooling it off.
Without cooling
unnecessarily.
Because traditionally people use the air conditioning when they're just trying to reduce the humidity, but then it gets cold,
Now you're on
as well, but you don't want to be cold. You want to
Right.
be this temperature. But I was at a house, they actually had a dehumidifier in the system, which was great. And I went around the corner and they had a humidifier on the same system.
Oh man, okay.
So somebody spent another $4,000 installing an additional $4,000 installing two systems that are actually competing against each other.
Wow. Comparatively, ballpark the system here is, as a frame of reference dollar-wise, what are we talking the differences either percentage-wise to a typical system?
Oh, we're generally around half.
Wow,
Yeah.
that's amazing.
Yeah, so this whole house for heating, cooling, ventilation, dehumidification was under $40,000.
So initial upfront is less, and then your efficiencies over the life end up being less on top of
less.
that. So
Yeah.
all in all, with these advances in technology is driving where you would think technology would drive pricing up to have a healthier home, you're actually saving.
Yeah, and we could have reduced those costs in this house by 12 to 15,000 because we had this air handler here, but there's a second one over there, which creates a second zone for these two guest bedrooms and a room over the garage.
Okay.
They're not using the space all the time. It gives them some flexibility and some control. So like if you wanted to make that space a different temperature, you could.
Got it.
But we could have, this system right here is actually big enough to run the whole house. And so the last few weeks while we were finishing the house, we had this system running. That one wasn't hooked up yet, and the whole house was the same temperature.
Why don't we talk a little bit about specifically the air quality system? The last time we were here, the Zender equipment was in the middle of the floor, nothing was connected. What are we looking at now? I see a lot of tubes coming out of this thing. It's a
This is fully installed now. So this is our ERV, our magic box. We've got these two main pipes here. This short one here is bringing fresh air into the house, and then this longer one here is exhausting the stale air out of the house. A technician from the manufacturer came down and spent 3 hours and they commissioned the whole system, which basically means they go into the control board here, they dial it into the specific house, and they take a flow hood and they go to every single register in the house. Because when you engineer airflow, every room, just like with heating and cooling, every room needs a certain number of CFM of air in order to maintain that comfort. And when you design ductwork like this, like these are smaller ducts and the larger ducts, because that's a much bigger fan motor in there. Every time you change the size of a duct, change it from sheet metal to a flex duct, put an elbow in it, the airflow changes.
So you've got to check each one individually as its own.
One of the things we do is when we engineer the heating and cooling systems, we actually hire a mechanical engineer that will design the ducts in our space. So they'll tell you, I want 20 feet of this size, and you're going to use this transition here, and then you're going to switch to this. We're going to reduce it to this here for 8 feet, and the last 3 feet are going to be flex duct to connect to this particular booth.
Got it. Jeez, real specific.
Yeah, but it's really easy to do. It cost us, I think, $2,500 to hire someone to do the duct design, all of the heating and cooling loads for the house, and design the system.
And then it's perfect.
Yeah, but it's installed. If it's installed to the plans, it's really good.
Yeah.
But then what this technician did, which our HVAC contractor is going to do as well, is we're going to take the flow hood and we're going to go over to each register and you put it right on there, and it'll tell you exactly how many CFM of air is coming out of it. Basically, with this system, that fresh air is coming in, going through here. See the arrows going up?
Yeah.
And these are all identifying all the rooms they're going to.
Yep.
So these 9 tubes here are all going to bedrooms and living spaces. So this is that fresh air coming in.
Okay.
And the other box in the back, we've got red tags. That's coming out of the kitchen, the bathrooms, and the laundry
Exhaust
room.
going
Exhaust.
Okay.
Yeah. So each one of these tubes is designed to carry approximately 12 CFM of air. But you can see, like that's our return register for the basement. So all the air in the basement's going through this system, and also through that system.
Okay.
So the temperature, humidity, and everything down here will match the house.
Wow.
So a lot of people they won't take the conditioned air in the basement and run it through their systems, and you end up, the humidity levels, especially in the summertime, can go up.
Yeah.
Same if you put your air handler in the attic, spray foam your roof, but then you don't run the air in the attic through the air handler, you end up with serious moisture problems in your roof.
Because you need to run it all.
I've consulted on multiple projects in South County where they literally had mold on the surface of their spray foam.
Wow.
Because they didn't.
The humidity level was so
just
high.
built up. Yeah.
Because that air wasn't included in the system.
Yeah, because it wasn't managed. A lot of people install ERVs today. A lot of HVAC contractors are starting to put them in. The building code outside of Rhode Island requires it. Rhode Island's eliminated that for some reason. But what they do is they take the ERV and they tag it into the ductwork that's already there.
Yeah.
Oh, we already got ductwork. Let's put it in there. Doesn't
Now,
work.
now you're inside the other ductwork.
Well, the reason it doesn't work is this is designed to run at about 130 CFM.
Right.
And it's going through little tiny ducts because that small fan, small duct.
Sure.
That duct, I mean, those are like
It's huge.
Yeah, they're like 10 by
Comparatively.
14. Well, that's a 600 CFM motor in there. So if you're trying to blow 100 CFM through ductwork that's designed for a 600 CFM motor, the air doesn't move. It's kind of like if I stand here and blow really hard, you'll never feel the air
Right.
move on the other side of the basement. That's essentially what happened.
But if you put it through a long straw, you
Yeah.
feel it on the other side.
Yeah, because the straw is designed for the motor.
I'm really looking forward to you taking us through the finished house now. Last time we were here, it was all rough and studs, but man, there are hundreds of feet of tube, and I'm seeing up here in the joists that you didn't have to do a lot of drilling of holes to get your ventilation through. Can you tell me a little bit about what we're looking at?
So these are, what was the manufacturer's name?
This
again?
looks like it says Triforce.
Oh, it's Triforce, yeah, Triforce. I discovered these about 12 years ago,
Okay.
and we've used them ever since.
They're open design joists, so you can run all of your...
Yeah, and they're not, I've used open web joists before, but they were custom. They came, a truss manufacturer would build them.
Okay.
These come pre-built. You're buying them right off the rack, just like a regular I-joist. And then the ends, the last 2 feet or so, or 3 feet, is a regular I-joist, and you can trim it.
So you can
trim it to
make
length.
it fit. So the time save on something like that must be incredible.
Oh yeah, I mean, you can look at how much stuff goes through. All the pipes go through there, HVAC goes through, all the
I
wires
see
go
wires
through there.
yeah, everything. So now
Everything goes through there.
Where you're able to, you're maximizing the headroom space in some of these areas, but you're not wasting all that time trying to cut through. And when you're cutting through a joist, you're modifying that joist. Now you're not compromising any of the
Yeah,
engineering.
I mean, regular I-joists, you can do pretty big holes, but nobody's cutting big holes in there. Actually, let me walk you through the water heater too, because there's a couple of interesting things we do differently. This is a heat pump hot water heater. So just we have a heat pump for the heating and cooling system. Same heat pump that's in your refrigerator, just slightly changed to work with the hot water heater.
Okay.
And this, like I said, has a filter. There's 2 grills up here,
Yeah.
and there's a filter in the intake air. So that has to get cleaned every so often. But basically, this is just pulling a little bit of heat out of the air and putting it into the water. So generally it will lower the temperature of a room 6 to 8 degrees or so. But the other nice benefit to it as well, when it's running through that heat pump cycle and creating that hot water, a byproduct of that refrigeration cycle is it creates, it pulls moisture out of the air, it's dehumidifying. So it naturally dehumidifies the basement as well. So that's why there's a condensate pump there. So as that's heating the water, it's gonna be pulling condensate out of the air and dumps it in there, and we pump it out. With this system, we kind of like the ventilation system, we kind of rule of thumb engineer it.
Yeah.
And the idea is that we design a house so the bathrooms and the kitchen are, especially the kitchen, are as close as possible to this, to
So
keep
that-
the pipe runs as short as possible.
Right.
The idea is that you're, 2 things is, one is, which is not as big of a deal here, like think if you're in the Southwest, water shortages, water is becoming a commodity. How much water do you want to go down the drain while you're waiting for the hot water?
Right, you don't want to
As
waste any
small
of it.
amount as possible. And then the other factor is you just paid all this money to heat your water up, and all that hot water that's left in the pipe when you turn the faucet
Sure,
off,
it's changing
it
temperature.
just cools off and then it goes down the drain.
You want it to get there fast.
hot water is there really,
Yeah,
really
yeah.
fast. And we go through, EPA has a water sense certification.
Okay.
So we go to the farthest faucet from the water heater,
Got
and we take a little calibrated bucket with a thermometer in it, and we've got to raise the temperature of 0.6 gallons. Has to go, in 0.6 gallons, you have to go up 10 degrees.
Okay.
That's the test to pass.
And if you get there,
then you're good.
You're efficient with the
it's
travel
part
of that
it's part
hot
of our
water.
certification that we run
Yep.
everything through.
Super.
And so in this house, we actually got to 10 degrees, and I think it was like 0.1 gallons.
So you beat it.
Yeah.
Yeah.
And 2 ways we do that. One is we design so that those runs are really short.
guess they're
But then we also, if you notice the pipe insulation, that's actually an R8.9.
Okay.
Whereas code's only R3. So instead of paying $1.50 for a length of pipe insulation, we pay $8. And the other cool thing I've learned from Gary Klein, is this guy's name.
Okay.
He specializes in water distribution, like residential and commercial, but he's like a total geek about water.
Okay.
And so what we learned was this is actually called an anti-siphoning loop. So the idea is that just like with air, You know, warm air is more buoyant. So if you have cold air and warm air, the warm air, like everyone says, it rises and it goes up. If you take a water heater, let's say, because you've got a hot water tap on the top here as well. So if you have that pipe going straight up, so what's going to happen is while you're not calling for water, this thing's just sitting here, the water up there is going to start cooling in the pipe. And then it's going to start sinking down into the tank. And as it goes down, it's going to be pushing hot water up.
So this loop,
that loop actually, it basically short circuits
cuts off the opportunity of it to go up.
Yeah, so let's say you're not using the hot water. This is the summer house, and maybe the hot water heater is on for a couple months. In between visits, you're not losing that little bit. And so why not? You just put that little pipe on
One
there.
little loop and you've got that extra efficiency.
Yeah.
It's an all-electric house. Can you show us the electric panel and how everything is tied together? There must be quite a bit involved if the entire system is operating out of electricity.
It's just a few more circuits is really all it is.
Okay.
I would say there's maybe like 10 circuits in here that maybe wouldn't exist
Okay.
if it wasn't an all-electric house.
Otherwise, it's pretty much an electric panel.
It's just an electric panel.
I will say a bit of a work of art the way it's all wired
Our
in
electrician's phenomenal. One of the interesting things though is when you get to an all-electric house, you're really, 200 amps is what we always put in. So as soon as you start getting your heating systems electric, your hot water is electric, if you don't design the loads to be really small, you're actually going to be pushing up to a 400 amp service, which for an average house, like right out of the gate, that's another $15,000 to $18,000.
So another benefit of maximizing that system and equipment.
Yeah, I mean that $15,000 is probably the additional installation costs, maybe. That's part of that designing. That design phase is we try to figure out that stuff ahead of time
And know what you're getting into when you design.
Yeah, because the last thing you want to do is you start doing the electrical work and then someone thinks they're going to be plugging 2 cars in. And no, you're not.
So let's take a walk through and see where our intakes and exhausts are for the air quality system. And then while we're at it, get a look at the house all finished up and done. Thanks.
Now we're in the finished house. So the ventilation system we were talking about, kitchen ventilation, we'll talk about the range hood in a few minutes, but this grill right up here, there's 3 tubes in the basement connected to that.
Okay.
So that's pulling about.
They're all coming in and
they're
sucking air out?
Yeah, so there's air coming out of that. The fresh air coming in is going through a MERV 14 filter.
Oh, so that's where it's coming in.
No, it's coming out of here, but the fresh air is coming in through that filter that's protecting the fresh air coming in. But the air going out, when it exits, it's getting pulled out of here about 32 CFM a minute, 32 cubic feet a minute, continuously. But there's a little filter in there as well, because when you're pulling air out of the kitchen, it's got grease and particulates and stuff in it.
You just don't want that getting in the vents.
We don't want to get it into the filter, or not the filter, the exchange core. Yeah, the exchange core where all the air goes through, you want to keep that clean.
Okay.
Yeah.
So yeah, because you wouldn't think, why filter the air going out?
Yeah.
You got to keep the equipment clean.
Yeah, that's one of the reasons why I like this system versus a lot of the other systems out there that people put in that cost a lot less money. They're not protecting the core. If you don't do the filtration, like, gosh, every 6 months you need to pull it out and clean the whole thing. Yeah, so that's exhaust air, because we're in a kitchen. And then you come over here, so now we're into a living room, and there's one of our fresh air grills.
Okay.
So that has 2 tubes attached to it.
All right.
So there's 24 CFM. If you reach up, you can feel there's like a little trickle of air. It's not a lot, like 24 CFM. It's not like you couldn't deliver heating and cooling with that because there's just not enough air.
It's not blowing. It's just coming in.
It's a slow amount of air over a continuously. Yeah, and then we've got another one over here in the dining room area, because this is actually, there's a lot of volume in here. We're trying to get all of the air in the entire house through that system, like so that the entire volume of air in the house once every 3 hours is completely removed and replaced with fresh air.
Right, we talked about that last time, and that's no small feat, and this is a big wide open house too. So this looks like a bit of a air traffic control system.
It is air traffic control, literally. So yeah, we've got all 3 of our systems are controlled here. This is our regular thermostat for the heating and cooling system. It's just a regular house, whatever you want to set your temperature to. The only thing different, when you change to heat pumps, you need to run it differently than a traditional heating system.
Okay, in what way?
Traditional heating system, heating and cooling in a normal code-built house is whenever you feel like, oh, I want to be warmer, you go and you raise it. Oh, I'm really hot, I want to be colder. You put the air conditioning on, you lower the temperature. And you basically can go up and down all over the place. With a heat pump, they're super, super energy efficient. One of the ways that you achieve their efficiency is by bringing a space to temperature and then leaving it there. So the whole idea is to set your temperature and forget about it. Like if you're boiling water for pasta, you turn the stove on and you put it on high, and there's a lot of energy going into that water, and then it gets to a boil. But most people realize, well, I can put it down to simmer, and the water's still boiling. So this system is designed to always be on simmer. It takes a lot less energy to maintain a boil at simmer than to maintain it at high. And that's why, for example, with a high performance home like this, if you add insulation to your walls, to your ceilings, to your floors, do better windows and make it airtight, you don't have those wild swings in temperature. So that just like boiling water, the first 5 minutes is really expensive, and once you get it there, it just stays and it's really cheap.
So the system's not constantly trying
you
hard
never, you never have that initial
fluctuations.
Yeah, you never have that initial boost in temperature. This is our dehumidistat. So the time of year when you don't worry about cooling, but you know, as the climate zones are marching north, like if you lived in Delaware or the Carolinas, Virginia Beach, there's a lot of times the air is super humid and you need dehumidification. That's like, if you want to be comfortable, that's what you need. You don't want it to be colder, you just want it to be less humid. Climate zones are marching north, and we're finding there's a lot of times in Rhode Island on the coast, especially here, like we're about 2 miles from Nittigrat Pond. So the summertime, there's a lot of humidity in the air.
Yeah, I bet. And you know, I remember my memories of dehumidifying a home is literally dehumidifier in this room with a hose to a bucket, or maybe it's going to the outside. And I've got one upstairs there, but the basement has two, and you know, that was the whole process. Yeah,
so this is running with our air handler, so that air that's going through the air handler is getting dehumidified.
And then,
so our ventilation control is the one up top.
All right.
So that's basically command center for that, but you really don't need to use it that much.
No.
Because the whole, just like the heat pump, it was engineered, set up, and then you turn it on and you just forget about it.
Right, you want it to be where it needs to be, and you shouldn't have to think about it.
It's already been engineered, and someone came in and set up the system from the company. So it's been commissioned, so you just forget about it. But sometimes, let's say you have a party, and you got 30, 40 people in the house, the CO2 levels in the house are going to start going up pretty quick.
They need more fresh air because they're using a lot of it.
So you go over to the control here, and there's a menu. You can actually put it into party mode. And what that will do is it'll actually boost the temperature up. And you can actually set it for a set amount of time.
Does it say party mode on it?
It literally says party mode.
All right.
But this system's also designed to work with a house with a fireplace. It's designed to work with a house. You could actually hook this up to your range hood.
In the rare instance that you do need to change the performance of what's happening for the cleaner, you can come over and just change the mode and then put it back to
because one thing, I've seen this happen in some houses with ventilation systems, if you over ventilate a house, and depending on how people live in the house, like a lot of houses, it changed during COVID because everybody was home all day. So the energy bills went up, like everything, the hot water was, we're running out of hot water now, we never did that before. But if there's only 2 people in the house, so there's a lot of volume in this house, if you over ventilate it, you could actually lower the humidity too much, which is a problem in the winter, because then you start getting dry mucous membranes, and you're more susceptible to viruses. So you can actually go over here and you could lower your ventilation to reduce that loss of humidity. And then the other thing you can do here too is, like, say you're going to be away for 6 months, or summer, or even like 3 weeks. You could just come over to that. Consuming. Just lower the ventilation rate. Like, why bother? You still should run it because the air gets stale. Because there isn't any natural ventilation.
So keep it on, but it doesn't have to be to the
just put it on the lowest amount. And
so you got party mode, away mode, and then everyday living mode.
And then the other feature this has, as you can see on the fan there's only one of the 3 bars is lit up, because I'm in the lowest mode right now. But in the bathrooms and in the kitchen, sometimes you want to increase the ventilation. So let's say you take a shower, there's a lot more moisture. There's a switch in the bathroom. You push the switch and it actually pushes it right up to the highest ventilation rate. So if the bathroom was at 24, it'll go up to like 36.
To move more air out.
And we have it set for a certain amount of time. So I forgot if it's like 30 or 40 minutes, it'll be in boost mode. And what that does is when you finish your shower, you leave the bathroom, all that steam is still in that space. So by leaving it in that boost mode, you're going to continue to ventilate an extra amount
Where normally
you
if I
left.
left the bathroom,
Yeah,
I'd probably just shut everything off.
Turn the fan off
and
and,
it's
you
still
leave,
steamy in
and
there.
it's still steamy. It's all stuck to the walls, and it's like, why do I have mold in my ceiling? It's because the water's still there. So there's a benefit to that. And then when you're cooking, we have the range hood, but maybe you're not. Maybe let's say you burned your salmon, or you're cooking bacon and you really don't want.
And you
to
want to just crank the air out. You can use.
Yeah, you can go over. And I'll show you. There's in the kitchen over here. There's one switch right here, right next to the stove. So if you wanted to boost this up, like we're at 33 CFM, you push this button, and now we go back over there, and you can see now our fan.
And now it's up to 3.
Boost mode, and it actually says 30. So it was a little 30 at the top. So it's going to be in boost mode for 30 minutes. When we first started building these houses, we didn't do an exhausted range hood. We always did recirculating, because one of the things we were concerned about is when you build a really airtight house, and let's say you put a 300 CFM range hood in, you turn it on, it's trying to push 300 CFM out, but that house is so airtight, there's no place for that air to come back in. There's no makeup air. In the residential building code, as soon as you get above 400 CFM, you're supposed to put in makeup air.
Okay.
Nobody does. People are starting to, but for you, I rarely ever see it.
All right.
In commercial code, there's always makeup air. So all those giant range hoods over those cooktops, like there's fresh air coming right into that hood. It's all part of the system.
Okay.
So what we started to do is we're ducting these out now. And what we did is we were creating makeup air systems to bring the air in. Just like the hot water heater, like we're putting the little loop on there to save that extra little bit, because we just learned about that. And it's like, why not? It costs another $50. With indoor air quality, we have our ventilation system, we've got our filtration on it. We're getting all this really good air, but then we are creating pollutants by cooking. So when you burn stuff, there's actually little particles that come out if you're into the air. They're called PM 2.5 particles, and they're so small they go right into your lungs.
Okay.
When you burn stuff, like just cooking oil, like that cooking oil is actually vaporizing and turning into little tiny particles. It's not like those things are going to kill you.
Sure.
But if we can effectively create one more layer of protection and it doesn't cost much money, like why wouldn't you do that?
Not to.
This one, we've got a hood liner in here.
Yeah.
And this is designed to only go up to 380 CFM. Because we don't need a lot. Like we made sure it was covering the whole cooktop.
Sure.
But what it is this is actually ducted out, goes out through the gable over there. And then this is connected with a low voltage wire to an electronic damper that's on another pipe that has air coming back in.
So it's immediately telling you, hey, we need to compensate for what's moving out.
Yeah, so as soon as you turn the hood on, it sends a signal to a damper that's up in the ceiling over there, in line with that pipe. It opens the damper up, and that basically creates an open 8-inch pipe that goes like from outside through the ceiling down the wall and comes out through the toe kick right here.
Right down the bottom. So, and it's right here,
right here.
where
So
it's being...
as that air is going out, fresh air is going to come in somewhere. That's the path of least resistance now.
Got it.
It's not perfect,
Right.
because if you're standing here and it's 12 degrees outside, yeah, it's going to be cold air coming
But it's
in
not,
here.
it's more perfect than opening up the window to try to fan on.
Yeah, and there's a new system we found that's really nice, but it's like another $1,500, where the makeup air damper actually has a preheater on it.
Oh, okay.
And it has a sensor on it, so it senses the outdoor temperature and it senses the exhaust air and the outdoor temperature, and then we'll ramp the heater up to try to...
So if it is in the winter time, you're not cranking in 20 degree
if it's 98 degrees and 100% humidity outside, you really don't want that coming in either.
Sure.
But that time of year, we've got a dehumidification system.
Yeah.
So it'll handle that.
Great, clever.
Yeah.
We still have a lot more to share on this deep dive with Steve and his crew, so we'll save that for the next episode. Make sure you subscribe and stay tuned for when that drops. So for now, I'm Tom with Arnold Lumber. We'll see you next time on Breaking Ground.